All right, let's unravel a fascinating scientific mystery about something you see and use every single day: water. So, let's kick things off with a puzzle, one you've probably wondered about before, maybe without even really thinking about it. With most substances, the solid form is denser than the liquid form, so it should sink. But ice doesn't. It floats. And that simple fact opens up an even bigger, more important question. I mean, think about it. If lakes froze from the bottom up, it would be a total disaster for everything living in them. They'd be wiped out every winter. So how do they survive? Well, the answer to both of these puzzles is hiding in one really unique physical property of water. Okay, so here's our game plan for this explainer. We're going to tackle this strange puzzle, get to the bottom of density and water's weird behavior, see how it plays out from the lab all the way to the oceans, and then finally we'll solve the mystery of how life survives under the ice. All right, first things first. To really get this, we need to talk about a concept called density. So what is density? Simply put, it's a measure of how much stuff is packed into a certain amount of space. The more mass you can cram into a box, the denser the substance is. And this is where water gets, well, weird. For most liquids, as you cool them down, they just get denser and denser. It's a straight shot. But water plays by its own rules. As you cool it, its density goes up, sure, but only up to a certain point. And that magic point is exactly 4 degrees Celsius. You have to remember that number. It's the absolute key to this whole puzzle. If you get any colder or any warmer than 4 degrees, water actually becomes less dense. How strange is that? So how is that even possible? Well, it all comes down to its volume. This graph shows that water's volume is at its absolute smallest at, you guessed it, 4 degrees Celsius. As it cools down even more, from 4 degrees towards 0, something amazing happens. The molecules start lining up to form a crystal structure, and that structure takes up more space. The volume actually expands. And if you have the same mass in a bigger volume, well, your density has to go down. Okay, so we've got the basic principle down. Now, let's see how this whole idea scales up, from a small instrument in a lab all the way to the massive oceans that cover our planet. So you might be wondering, how do scientists actually measure this? They use this really clever tool called a hydrometer. It's basically just a weighted glass float. You gently lower it into your liquid, give it a little spin, and the denser that liquid is, the higher the hydrometer bobs up. It's a really simple but super elegant way to get a precise reading right off the scale. Now, let's zoom out, way out. In the ocean, density isn't a single number. It's a constant dance between 3 main factors. You've got temperature, which we've already talked about. Then there's salinity, basically how salty the water is. And finally, there's pressure, which of course gets higher the deeper you go. And these tiny differences in density are the engine behind the massive ocean currents that circle the globe. Think about it. Colder, saltier, denser water sinks, and warmer, less dense water rises. This creates a gigantic global conveyor belt that acts like our planet's thermostat, moving heat around and regulating our entire climate. All right, time to bring it all home. Let's solve that mystery we started with. How does this peculiar property of water actually protect life? Okay, picture a lake as winter rolls in. The air gets cold, which cools the surface water. As that surface water cools towards 4 degrees Celsius, it gets denser, so it sinks. And that pushes the slightly warmer, less dense water from below up to the surface. This whole cycle of sinking and rising continues over and over until the entire lake, top to bottom, has reached our magic number, 4 degrees Celsius. So now what you have is this big, stable reservoir of the densest possible water at 4 degrees, all settled in, nice and cozy, at the very bottom of the lake. And now the strange part kicks in. As the surface keeps getting colder, dropping from 4 degrees towards 0, the water actually becomes lighter. It's less dense. So it stops sinking. It just stays right there at the top. And finally, when that top layer hits 0 degrees Celsius, it freezes solid. Because of that crystal structure we mentioned, ice is about 9% less dense than the liquid water beneath it, which of course is why it floats so well. Now, here's the crucial part. That sheet of ice acts like a perfect insulating blanket. It shields the rest of the water from the freezing cold air above, and that's what prevents the entire lake from turning into a solid block of ice. And this is the beautiful result. This one unique physical property allows fish and all the other aquatic life to survive in a relatively stable 4-degree environment at the bottom, safe and sound all winter long. It's just an incredible, life-sustaining feature of the most common substance on Earth. Water's anomalous density is just one of its many incredible characteristics. What other unique properties of water can you think of that make all life on Earth possible? If you found this explanation helpful, don't forget to hit that like button and subscribe for more.